Hello, everyone. Good afternoon. Welcome, welcome. Glad to see you. Hope you had a great weekend. We are, as you saw, chat a little bit here, we are in the final stretch of this class, if you can believe it. But that's where we are. So a couple of quick things. Exam number 3, all right, will be on Thursday, April 29th. And it'll be set similar format to the previous exams, and it'll cover chapters 19, 20, and 21. Okay, so have that on your radar. A few days after that is the final. That'll be on Monday, May 3rd, and that'll be cumulative over the entire semester. So everything we've covered over the semester will be on the final. All right, so the two things you have coming up, you put a lot of work into this class and you just have a little bit to go. And I know it's tempting to kind of coast a little bit, but don't do that, because you've made a big investment, and it'll be worth the payoff if you just stick in there until the end. All right, and then you'll have lots to celebrate come May 3rd. All right, because then you'll be done, and you will have done your best, right, in a very tough year. So congratulations on getting this far, and we'll soon you'll soon be completely finished. So good job. Before I get started, do you have any questions for me on anything? Just a note about the final. The final, just like exams, you'll be able to have a one page of notes that you can have with you, right? And you'll have the same periodic table and the same table of constants. All right. So it'll be similar. It'll be similar in format to our normal exams. It'll just cover more material and be a little bit longer in length. Okay. Yeah, I think for the problem set, let's wait till after class, and I'll be happy to take your questions from the problem set after class. Okay, if that's okay with you. Let's see, any other questions? I'm a little bit curious, so I want to ask you a question about vaccines. I'm just kind of curious where we are in terms of, students of your age or students at SPCC that might be coming back next semester. Where are we on the vaccine? So I'm going to just do a poll here on this question, and just let me know. And maybe the rest of you are curious too, but I'm kind of curious to know where we are on vaccine. So answer this question if you don't mind. I don't track these or anything, so I'm not going to track you, obviously, but I'm just kind of curious to know where people are. Wow, okay, that's super interesting. So it looks like about 70% of you either have an appointment or you have a vaccine. That's awesome. That's really great to know. Well, good job on getting your appointments. If you haven't been able to get an appointment yet, hop on there and try to get vaccinated. The more of us that are vaccinated, the sooner all this will be over, and the sooner we can get back to our normal lives. So, but good job on that. I know it's not easy to get an appointment, but they're now available, I think, to everyone of every age above 16. So you should be able to get one. If not soon, if not right away, then very, very soon. Great. Okay, let's pick up where we left off last time. Yeah, 80% for herd immunity. That's right. So, hey, we can meet as a class almost. Wouldn't that be fun? Yeah. Let's see. So remember, standard electrode potentials we finished off there last time, right? And that's a table that looks like this, right? that lists a bunch of half reactions. They're all written as reductions, but they can occur in either direction, right? They're just written as reductions by convention. Those half reactions at the top of the list, right, have a very positive reduction potential. Remember that does the positive charge attract electrons or repel them? Attract, right? So one way to remember this is if you have a very positive standard electrode potential, that means you have a strong tendency to attract electrons, right? Which means you'll tend to undergo reduction, right? And if you look at the thing at the very top of the list, that kind of makes sense. Fluorine is very electronegative. It has a very positive reduction potential, and it tends to undergo reduction, right? It tends to attract electrons to itself. As you go down the list, things get more and more, less and less positive, or more and more negative, right? You get to hydrogen, that's what we said is 0. That was sea level, this particular electrode, all right? And then you get down below sea level and you get to all these negative reduction potentials. Negative charge, of course, repels electrons, right? So things on the bottom of the list tend to go in what direction? Oxidation or reduction?
Oxidation.
Oxidation, okay? And it's no surprise that almost everything below hydrogen on the list is a metal. What do you know about metals?
They like to lose electrons.
Yeah, they have a tendency to lose electrons, right? So it's no surprise that things towards the bottom of the list are mostly metals, all right? And they tend to undergo oxidation, okay? The reverse of the reaction as written here, right? So remember, things with very negative potentials tend to go oxidation. Things with very positive potentials tend to undergo reduction, okay? All right. And then remember, we also, from last time, we learned how to calculate E cell, which is the voltage of an electrochemical cell, right, from that table. And remember what you do, you figure out, okay, what's being oxidized, what's being reduced, right? So you write out those reactions. And then oxidation occurs at the anode and reduction occurs at the cathode. And you just subtract out whatever value is here for the cathode minus the value for the anode. And that gives you E0 for the cell, right? And what did we learn? We learned that a positive E0 cell means that the reaction is spontaneous, as written in the forward direction, and a negative E0 cell means the reaction is not spontaneous. Okay. You guys hear me okay? Great. Okay. Good. So we did some examples and I asked you a question and most of you got that right? The answer is 2.71 when you figure it out this way. And then I think this is where we left off, was predicting the direction of reaction. So for example, if you know you have an electrochemical cell that consists of 2 half cells, all right? And you know that 1 half cell is, let's say, nickel and nickel 2+, and the other half cell is manganese and manganese 2+. In which direction will the spontaneous flow of electrons occur, right? In other words, which of these 2 reactions will be the anode and which one will be the cathode if we just let it go spontaneously? Well, we just learned, right, that a very negative E0 tends to undergo oxidation, right? So you could remember negative is oxidation. This is just kind of a way to remember that. Negative is oxidation, and positive is reduction, right? So you look at the 2 reduction potentials and you look for the more negative one, and the more negative one is going to be the reaction that occurs at which electrode, the anode or the cathode?
The anode.
Correct, the anode, right? The more negative one is the one that occurs at the anode, okay? And the more positive one or the less negative one is going to be the one that occurs at the cathode, right? So in this case, right, if you had an electrochemical cell, right, that had manganese 2+, this reaction, nickel 2+, right, this reaction, we would find that the manganese is the one that acts as the anode, okay? And electrons will spontaneously flow from here to here, okay? if we write down those two half reactions and we figure out E0 cell, right? We know that this will undergo oxidation. So this is the reaction that occurs at the anode, right? The nickel will undergo reduction. So this is a reaction that occurs at the cathode, right? And we put in those E0s, we look them up. And then we just say E0 cell is cathode minus E0 anode, right? We plug those numbers in and we find that in fact, E0 cell is positive, right? And remember what a positive number means.
Spontaneous.
Spontaneous, correct, right? For an electrochemical cell, a positive voltage means it's spontaneous, okay? So just summarizing this idea, right? The half reaction with more positive electrode attracts electrons and undergoes reduction. The one with more negative repels electrons and undergoes oxidation, right? And then here's an interesting little tidbit that really helps. Any reduction on the table, right? In that table of half cell potentials, any reduction is spontaneous when paired with the reverse of any of the reactions listed below it, right? So in other words, any one of these reductions that are here are spontaneous when paired with the reverse of a reaction below it, right? And that's again because things towards the top of the table tend to go in the forward reaction, things in the bottom tend to go to the reverse reaction, right? So when you pair any reaction with one below it, it'll be spontaneous, all right? It'll undergo reduction and the one below it will undergo oxidation, all right? So that's kind of convenient, because then we can predict things like, oh, I have a question for you first. Yeah, let's answer this question and then we'll go on to predicting some other things. Go ahead and see if you can answer this question for me. Yeah, and here are these are the potentials, so. Okay, I'll stop it there. And it looks the right answer was B. So we got about 62% of you guessing B, or choosing B, so that's pretty good. Some of you chose A, so let's just have a quick look at this and say why it's B and not A. So remember NEO and PER, okay? Negative is oxidation, positive is reduction, right? So if you're looking at two half reactions and you're trying to decide which one's going to go oxidation, which one's going to go reduction, right? Just remember NEO and PER, right? Negative is oxidation. So which one's more negative? This one, right? So this is the one that's going to undergo oxidation, right? So that's one thing you got to remember. The other thing you got to remember, of course, is that oxidation occurs at which electrode?
The anode.
The anode, right? So just remember this, oxidation occurs at the anode, right? And oxidation and anode begin with vowels, right? So that's kind of makes it a little easier. Reduction occurs at the cathode, right? And those both begin with consonants, right? So that's a way that you can remember this, okay? So when you're trying to decide, just remember the more negative one is the red cat for reduction at the cathode. There you go. I like that. Red cat, right? What is that breed of cat that's kind of orangey red? Garfield.
Garfield?
Yeah, Garfield, but isn't that a Garfield is, yeah.
You're talking about calico?
It's a tabby. What? Tabby. So you guys just remember red cat, reduction at the cathode or oxidation at the end. Okay, good. Any questions on this? Is this making sense? All right, awesome. You could also use the table of electrode potentials to predict whether a metal will dissolve in an acid. So when a metal dissolves in an acid, let's say you have something like copper, right? No, actually I don't want copper. I want something like iron. Or let's say zinc, easy one. Zinc goes to zinc 2+ plus 2 electrons, right? That's the reaction by which a metal dissolves in an acid, right? And so that's an oxidation, right? So the reduction that causes that in many acids is H+ plus 2 electrons goes to H2 gas, okay? And we know that E0 here is 0.00 volts, right? And that's the reaction that drives the oxidation. So if we go back to our list, right, we said that any reaction in the table is spontaneous when paired with one below it, right? So this makes this really straightforward. If this is the reaction that drives the oxidation, right, in an acid, right? If this is the reaction that drives an oxidation in an acid, then which metals will dissolve in the acids, in these type of acids?
All the ones with a negative delta E cell.
Correct. Exactly right. All the metals below this half reaction will be spontaneous, right? In other words, any reaction in the table is spontaneous when paired with the reverse of the reaction below it. So notice all of these oxidations under all these metals, right? So if I put iron in hydrochloric acid, it's going to dissolve. Lead, tin, nickel, cadmium, so on. All these metals will dissolve in hydrochloric acid, right? Will copper dissolve in hydrochloric acid?
Nope.
Nope.
No.
No, right? Because this will be spontaneous only with metals below it, right? With half reactions below it. Since it's above it, if you pair these two, you're going to get a negative E0 cell, which means that it's not going to happen, right? It will not dissolve, okay? So for acids such as HCl, HBr, HI, the reduction reaction, or let me write it this way. The reaction that drives the oxidation of the metal is H+ plus 2 electrons goes to H2 gas, right? So it's that reaction. But for nitric acid, the reaction that drives oxidation of metals is this reaction right here. NO3 minus plus 4H plus 3 electrons goes to NO plus 2 H2O. Okay. So nitric acid is a little bit different. Notice that nitric acid, right, has a more positive half cell potential than the other acids, such as that depend on H+. Okay. That means that nitric acid can dissolve some metals, right, that hydrochloric acid wouldn't be able to dissolve. Okay. So which metals can nitric acid dissolve? Let's go down the list here. Silver, copper, copper's right there. And then of course, all the other metals as well, right? In other words, nitric acid is a stronger oxidizing agent. It is more able to cause the oxidation of other things, right, than these other acids such as HCl, HBr, or HI. Okay, so nitric acid is a little bit of an exception. Okay, so let's see if that's making sense. Let's see, go ahead and try to answer this question.
Is there any way you can zoom in a tiny bit on your chart?
Yeah, let me try that. Is that better?
Yeah.
So just as a reminder, nitric acid uses this half reaction right here as the reduction, right? This is the reaction that's happening when nitric acid dissolves metals. This is the reaction that happens when hydrochloric acid dissolves metals. Okay? And also just, if you haven't voted yet, please go ahead and vote. Remember that the important idea here is that any reaction on this table is spontaneous, right? In the forward direction that is listed when it's paired with the reverse of a reaction below it. Okay, any reaction on this table is spontaneous when paired with the reverse of any reaction below it. Good. All right, I'm going to end it here. So the right answer was B. You can see here that most of you got that. So very, very good. Because remember that here's the reaction that is responsible for the oxidation of metals in nitric acid, right? Here's the reaction in hydrochloric acid. So basically, which of these metals that are listed here will dissolve in this, but not in this? So it has to be a metal that's between here and here, right? So if you look down, the only one on this list that's between here and here is silver, which is right there, okay? So in other words, silver will dissolve in nitric acid, but it won't dissolve in hydrochloric acid. Okay, Sophia, did you have a question?
Just in general, when they oxidize, they dissolve.
Yes, yes, because the metal goes from being a solid, right, which just sits in the solution, to an ion which dissolves? Great question. Absolutely. That's exactly right.
Thank you.
Okay, good. Good. Any other questions? Is that making sense? Okay, let's move on to look at the connection between cell potential, free energy, and equilibrium. So we already know that a positive cell potential tells you what about the electrochemical cell?
Spontaneous.
Spontaneous, right? So what can you predict about delta G for that electrochemical cell if it's spontaneous?
It's negative.
Negative, right? Because we already know that delta G has got to be negative for all spontaneous reactions. So we actually have these three quantities that are all interrelated, all right? And they're interrelated in ways that kind of make sense, right? So we already learned about delta G, right? A negative delta G is spontaneous. So spontaneous, let's write this. For spontaneous, let me make this a little smaller here. So for spontaneous processes, we have delta G 0. And let me say, let me be a little more clear. Let's say spontaneous under standard state conditions. All right, so in other words, when everything's equal to 1 molar or 1 atmosphere, right? What do we know about delta G? We know that delta G is less than 0 for spontaneous reactions, right? What do we know about E0 cell for spontaneous reactions?
Positive.
Positive.
Greater than 0, right? And what do we know about K for reactions that are spontaneous under standard state conditions?
Is it greater than 1?
Greater than 1.
Greater than 1.
Exactly right. Right? K is greater than 1. Because remember, under standard states conditions, what's Q equal to?
K.
Under standard state conditions, what's Q equal to?
K. Oh, 0.
0.
No.
Not 0.
Wait.
1. 1.
1. Right? Remember that if you have a reaction A in equilibrium with B, right? Q is equal to the concentration of B over the concentration of A, right? So if everything is 1 molar or 1 atmosphere, what is Q under standard state conditions?
1.
1.
Right? It's always 1 under standard state conditions. So if delta G is less than 0, right? We know that that's going to be spontaneous under standard state conditions, right? Which means it's going to go to the right, which tells us that K is going to be greater than 1, right? And you can also see that relationship right here. This is the equation we learned earlier, right? Relating delta G 0 to K, right? So if this is, if delta G is a negative number, then K is going to be greater than 1. If delta G is a positive number, then K is going to be less than 1. So you can see that from this equation, but you can also think about it conceptually, okay? Now, this is the relationship right here. These two relationships we haven't covered yet. So we've looked at this one already. Let's look at this one. This tells us that delta G naught is equal to minus N F E naught cell, okay? Where N is equal to the moles of electrons transferred in the reaction. And F is a constant called Faraday's constant, okay? And Faraday's constant has a value of 96,485 coulombs per mole of electrons, okay? Faraday's constant is basically just the charge, the total charge of a mole of electrons, or the absolute value of the total charge of a mole of electrons, okay? So notice if E naught cell is positive, what's the sign of delta G naught?
Negative.
Negative, right? just like we predicted here, right? These are going to be opposite in sign, one from the other, right? Okay, so let's do an example. Let's calculate delta G for this reaction from E0 cell using this equation, okay? So first of all, what's the oxidation reaction that's occurring here? What's being oxidized, tin or iron?
10.
Tin, right? Tin. 3 SN solid goes to 3 SN2 plus 6 electrons, okay? And we of course know that oxidation occurs at the anode, right? Then the reduction half reaction is 2Fe3 plus 3 electrons goes to 2 Fe solid, right? And that's a reduction, so that's the reaction that occurs at the cathode, okay? Then we look up the values of E0 for these reactions in the table, right? Just look on this table. So for tin is right here, right? To tin 2 plus. So that's equal to what? Negative 0.14 volts. Negative 0.14 volts. And then we look up iron to iron 3 plus, and that's right here. That's equal to negative 0.036 volts. Okay. So then from there, we can get E0 cell, right? Is equal to E cathode minus E anode, right? So cathode is minus 0.036 volts minus negative 0.14 volts, right? And that's equal to 0.104 volts. Okay. So that part you already knew how to do, right? You've done that. You did some of that on your problem set, correct? Oops, thank you. 6 electrons here. Thank you for correcting me. The next thing is now we want to plug into this equation right here, right? To get delta G, right? To get, oh wait, sorry, not that equation. We want this equation, right? E0 cell is equal to 0.0592. No, sorry, no. First we're doing, hold on for a second. First we're calculating delta G, and then we'll calculate K. I got ahead of myself, right? First we'll calculate delta G. So delta G naught is equal to minus N, okay? N is the number of moles of electrons, so what would it be for these two reactions?
6.
6, right? So we got 6 moles of electrons, right? Times Faraday's constant. So this is 6 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electrons, right? Times what?
Times E cell.
Yep.
E not cell.
0.104 volts, which is what we just calculated, right? So notice what happens, right? Mole of electrons cancel, right? And do you remember what a volt was?
The potential of current? Or the
Yeah.
potential?
But it's not a fundamental unit, right? 1 volt is equal to what? 1 joule per coulomb, right? So we can write joules per coulomb here, and then the coulombs cancel, right? Which is how we end up with units of joules, which is what we expect for delta G, right? So when we multiply that out, we get negative 6.0 times 10 to the 4th joules. Does that make sense? And we saw, right, E cell was positive, delta G is negative, delta G naught is negative. Okay. Rylan, did you have a question?
Yeah, on the chart for our voltages,
Yeah.
all those equations are always factored, right? So like, why is it that we use the 6 electrons here when the equation that we were working with would factor a 2 out of that?
Correct. So that's where this table is a little bit different than the tables, let's say, of enthalpies or free energies, where you always multiply by the number of moles of the reaction. But voltage, because it's joules per coulomb, it's more like density, right? You don't double the density of something if you have twice as much of it, okay? But you do, in the case of delta G, you do have to multiply times the number of moles of electrons that get transferred in the reaction, right? If you're going to get the correct value for joules. Because joules is not like density. Joules depends on the amount. So that's why you have that there.
Got it. Thank you.
Does that make sense?
Yeah, it does. Thank you.
Taylor?
So to add on to what Rylan was kind of talking about, so the voltage is not dependent on your number of mole or your number of moles, but
Correct.
this equation accounts for that.
Correct.
So that makes delta G all good as far as how many moles you have. Okay.
Exactly right.
Okay. So when we're calculating this, that's already figured out basically into the
Right.
equation. Okay.
Yep. So okay. So notice that we can get delta G from E naught zero cell. Okay, and that is using this equation right here. Okay. The other equation from this, who was that? Taylor called the Bermuda Triangle of equations. I like that. The other equation is a relationship then between E naught cell and K, right? Because if delta G and E naught cell are related and delta G and K are related, then of course K and E naught cell are also related, okay? And so that equation is E naught cell is equal to 0.0592 over N times the log of K. Notice that this is base 10 log, all right? And this is super confusing. Some of these equations use base 10 log, some of them use the natural log, okay? Okay, someone asked me, does the sign of the standard potential ever get reversed if the reaction is oxidation instead of reduction? The answer to that question is no, all right? It doesn't. Even though some books improperly and incorrectly specify that. Okay, so you may have used a book in the past that made you change the sign if it's oxidation instead of reduction, but that's not the right way to think about it, nor is it correct. The right way to think about it is that these potentials are for these systems, right? And then if you just always write E cell is equal to E anode minus E cathode, that'll work out. If you change the sign of it and do E cell is equal to E anode minus E cathode, you'll get the wrong answer. Okay, so the correct way to do it is to never change the sign of these. Just keep the sign the same no matter what it is, and then do E cathode minus E anode, and you'll always get it right. Okay, but like I said, there are some books that teach it wrong. But this is the way electrochemists do it, right? And electrochemists are the professionals, so we'll follow their lead. All right, good. Any other questions? Okay, so relationship between E cell and log K. So let's, for this reaction that we just calculated delta G, now let's calculate K, all right? We already know E cell because we had it from the first part, right? E0 cell was equal to plus 0.104 volts, right? We calculated that in the previous example. And now we just want to calculate K, right? So we'll use this equation, right? In this case, again, N is going to be equal to 6 moles of electrons, right? 0.0592 is a constant that is a result of putting together several constants, okay? So what we want in this case is K, right? So the log of K is going to be equal to E0 cell, right? Divided by 0.0592 over N, all right? And so that's going to be equal to 0.104 volts divided by, well, wait, did I do that right? Log K, E naught cell. I think I have a mistake here in my notes. Hold on for a second. Divided by that, divided by that. Yeah, perfect, okay. So that's equal to 0.014 volts divided by 0.0592 over N, 6 moles of electrons. And in this case, because this constant was worked out from a bunch of different constants, you just have to remember that the log of K is going to be a unitless number, okay, because K is unitless, okay? And so that's equal to 10.5, all right? So K is going to be equal to the inverse of that, which is 10 to the 10.5, which is equal to 3.5 times 10 to the 10. And let's see if this all makes sense. What did we get for E naught cell? What kind of a number?
We got
Positive.
a positive number.
Positive number, right? Which tells you it's spontaneous. What do we get for delta G?
Negative.
Negative number.
Negative number also tells us it's spontaneous. What do we get for K?
Something
Bigger
bigger
than
than
one.
Than 0.
Something bigger than 1, right? Which tells us that it, again, is consistent with it being spontaneous under standard state conditions, okay? So really think about all this in your mind and how it all comes together, right? This Bermuda Triangle of equations, right? They're all interrelated and you can think about them all conceptually. So let me ask you a question and see if if you're getting that. Go ahead and answer this question. Okay, go ahead and vote if you haven't yet. All right, time. Very, very nice. The vast majority of you got that right. So that is awesome. Awesome, awesome, awesome. The right answer was C, right? K is greater than 1, E0 cell is greater than 0, right? Because a negative delta G tells you the reaction is spontaneous under standard state conditions, right? That tells you that K is greater than 1 and E0 cell is positive, all right? So you're getting the connection between all of those. Nice job. Yes, if you can find one, you can get them all. It's correct. They're all, because they're all interrelated. Absolutely right. Okay, good, 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 good. All right, any more questions about that before we turn to non-standard conditions?
I had a question. Would it be flipped if delta G was positive? So that would mean that
Delta G was positive. Let's go through this and see what would happen if delta G was positive. If delta G0 greater than 0, right? That tells you that the reaction is non-spontaneous under standard state conditions, right? So what does that tell you about E0 cell? Positive or negative?
plus negative.
Less than 0, right? And what does that tell you about K? If it's non-spontaneous under standard state conditions, that means that it's going to the left under standard state conditions, which tells you that K is
More than 1.
not more than 1, less than
Oh,
1.
less than 1. Yeah.
Yep. Yeah. Good. That's exactly right. Okay, let's think now about non-standard conditions for a moment. So remember that little 0, right, that we sometimes ignore, but it's actually very important, right? That little 0 there tells you standard state conditions, right? That little 0 there tells you standard state conditions, right? What if you don't have standard state conditions? What if the concentrations are something other than 1 molar or the pressures are something other than 1 atmosphere? So for example, here we have an electrochemical cell that we've seen since the very beginning, zinc going to zinc 2+, copper 2+ going to copper, right? And we know that E0 cell for that cell is 1.10 volts, okay? Now, what happens if...
Wait, Tro, what would Q be for the reaction not spontaneous under standard state?
Remember that Q... So when things are in their standard states, right, what's the value of Q?
1.
1.
Right? Q is always equal to 1. So under standard conditions, Q is equal to 1. Is that what you were asking?
Yeah, thanks.
Yeah, good. Okay. So non-standard conditions. So here we have standard conditions. We know what E cell is. We know how to calculate that, right? But what if, for example, we take the same cell, but instead of having the copper 2+ concentration be 1 molar, we have it be 2 molar. All right. And instead of having the zinc 2+ concentration be 1 molar, we have it be 0.010 molar. In other words, we reduce this concentration down to, this is the standard conditions. We reduce this concentration to 0.01 molar. We increase this concentration to 2 molar, right? What happens to the voltage? Well, before we answer that question, what do you think is going to happen? Notice if I increase this from 1 to 2, decrease this from 1 to 0.01, is this reaction going to get more spontaneous or less spontaneous?
More spontaneous?
More spontaneous, right? Absolutely, more spontaneous. Why? Think of Le Chatelier's principle, right? You increase the concentration of the reactant, decreasing the concentration of the products, right? So you would expect it to be more spontaneous. If it's more spontaneous, what do you expect to happen to the value of the voltage?
Increase.
Increase. Exactly right. You would expect the value of the voltage to increase, and that's exactly what happens. Okay? Here it's 1.10 volts. Here it's 1.17 volts. All right? So the voltage has gone up when you change the concentrations like this. So the question becomes, well, how do we calculate E cell under non-standard conditions? Sophia.
More spontaneous doesn't mean it's faster, right?
No. So don't remember our big picture idea of the difference between kinetics and thermodynamics, right? Kinetics determines what? How fast. Thermodynamics determines what? How far. Okay, so kinetics, how fast. Thermodynamics, how far, right? So anything related to delta G and entropy and delta H, right? That's thermodynamics. And that's not telling us anything about how fast a reaction occurs. It's only telling us about how far a reaction goes. So these are two separate things, right? Remember my example of diamond turning to graphite? So that reaction is spontaneous. Diamonds will spontaneously turn to graphite, but yet you may have a diamond on your finger right now and doesn't seem to be turning to graphite, right? Why is that? Because the reaction is very, very slow, okay? The kinetics are super slow. Why is that? Because it has a huge activation barrier, right? So kinetics are determined by activation barriers. Thermodynamics are determined by the relative free energies of the reactants and the products, okay? So they're separate. And so what we're talking about here is how far, not how fast. Does that make sense? Thanks for asking that question.
So just to clarify, like if you do what you did now and it's more voltage, then it's just mean there is more being converted to the reactant, to the products?
It means that the reaction has it's kind of like, so think about our analogy for voltage, right? Our river analogy, right? Voltage in an electrochemical cell is like the steepness of the river, right? The driving force that drives the water forward. So by changing these concentrations, we've made the driving force stronger. It's like making the river more steep, right? So it'll drive more current because ultimately it'll go further to the right than this one would have. Does that make sense?
I guess I just like, when I picture that, I kind of picture it going faster too.
I know, you're right. So the analogy breaks down there. Yeah, you're right. The analogy kind of breaks down there. Good point. So no analogy is perfect, and that one certainly isn't as well. But I want you to, at the same time that you think about the river analogy, you got to balance that with the idea that we're talking about thermodynamics here, and thermodynamics tells you how far. Okay?
It would be more like you can cover a longer distance of the river.
Let me think about this for a minute. What would it be? I would just think about it in terms of driving force, like how much driving force do you have for the reaction?
Okay.
You have more when you change the concentration this way. If you would have changed the concentrations the other way, right? If you would have made this 0.01 molar and this 2 molar, then you would have a lower voltage, right? So a lower driving force for the reaction. Taylor, did you have a question too?
Yeah, I kind of had a question with the concentrations.
Yeah.
So you doubled one, but divided the other one by 100.
Yeah.
And the voltage is not that big of a change. If you were somehow able to make it like equal proportion, like, how do I say this? Since you doubled one, which is like less of a change than the other one, is that like limiting how much that change?
Sure. Yeah. If you increase this by a factor of 100, then the voltage would also increase even more. But you're very perceptive to notice that we made some big changes in concentration, and the voltage didn't change all that much, right? And that's because it's a logarithmic relationship, right? So we'll see the equation here. The equation here that governs this. Well, actually, before I show you the equation, let me remind you of an equation for delta G for non-standard conditions. Do you remember what that was? Under non-standard conditions, delta G is equal to delta G naught plus RT ln of Q. And there's the logarithmic relationship to the concentrations, right? And so that's why a change in the concentration does not necessarily create a big change in delta G. It does create a change, but in the electrochemical cell, it's a similar equation, right? So that's the equation for delta G. Here's the equation for voltage, E0 cell minus 0. So E cell under non-standard conditions, right? 0.0592 over N times the log of Q, right? So notice the similarities here, right? Delta G E cell, delta G naught E naught cell, and then you have a constant times, in this case, the natural log of Q, in this case, base 10 log of Q, all right? And again, this is just the way the equations are written by convention, okay? One is natural log, one is base 10 log, right? So be careful with that, okay? All right, so if we go back to our Bermuda triangle of equations, right? We can add this equation here at the bottom, which is the equation for E cell under non-standard conditions, all right? So all of these equations are important. I expect you to know them all for the exam. So let's do an example. Let's calculate let's calculate the cell potential, right? For this redox reaction, first under standard conditions, right? And then under non-standard conditions, okay? So we'll start with standard conditions. Oxidation is what?
The magnesium.
Correct. Magnesium, 3 magnesium goes to 3 magnesium 2 plus 6 electrons, right? Because I need 6 electrons to make it neutral. And then the reduction is the iron, right? 2Fe3 plus going to 2Fe solid. Oops, and I forgot the 6 electrons here. I'm gonna squeeze them in, okay? So this is the anode. This is the cathode, right? We look up the half cell potentials for these, right? For the magnesium, it's minus 2.37 volts. For the iron, it's minus 0.036 volts, right? Those are the half cell potentials, okay? So E cell is equal to E cathode minus E anode, right? And that's equal to negative 0.036 volts minus negative 2.37 volts. And we get a whopping 2.33 volts. So what do we know about the reaction?
It's very spontaneous.
Very spontaneous, right? Has a very positive voltage, okay? So for part B, right, we're gonna use this equation, right? So we gotta find Q. Let's just calculate Q first. Q, let's look at the reaction. Q is equal to the concentration of magnesium raised to the third power, right? Because of that 3, divided by concentration of Fe3 plus raised to the second power, right? Of course, the solids do not go into the equilibrium expression, right? So they don't go into Q, right? So if you determine Q, that's going to be equal to 2.50 the quantity cubed, right? Because it says that's 2.5 molar, and then the concentration of Mg2 plus, sorry, the concentration of Fe3 plus is 1 times 10 to the minus 3. The quantity squared, right? So cube is equal to 1.56 times 10 to the 7, okay? Before we actually calculate E0 cell, again, let's think, what do you think? Is it gonna be more spontaneous or less spontaneous under these conditions than it was under standard conditions? More spontaneous or less spontaneous under these conditions than under standard conditions?
More spontaneous.
Okay, let's see. Fe3 plus. Remember, standard conditions, the concentration of Fe3 plus is what? 1 molar. Under these conditions, Fe3 plus is 10 to the minus 3 molar, right? Under standard conditions, Mg2 plus would be 1 molar, but now it's 2.5 molar. So what do you think? More spontaneous or less spontaneous?
Less.
Less, correct. Less spontaneous under these conditions than standard conditions. So we would expect E cell to be what compared to 2.33 volts? Bigger or smaller?
Smaller.
Smaller, correct. We expect it to be smaller, okay? So let's calculate it. E cell is equal to E0 cell minus 0.0592 over N times the log of Q, right? We know E cell was 2.33 volts. Sorry, E0 cell was 2.33 volts minus 0.0592 over N. What's N for this reaction?
6.
6, right? It's this number right here, okay? Over 6 times the log of Q. We calculate Q 1.56 times 10 to the 7, right? So that becomes equal to 1.90 volts. So it is in fact smaller, just like we predicted.
Question.
Yeah. Sophia?
So it depends on if you're raising the cathode and reducing the concentration of the anode. How's that relation?
Yeah, so just the best way to think about it, I think, is like kind of like with Chatelier's principle. If you raise the concentration of the reactants and lower the concentration of the products, that's going to be more spontaneous. If you lower concentration of reactants but raise concentration of products, that's going to be less spontaneous. Ryland.
So it looks like based off this equation, is Q is going to control the sign of that second term of that equation. So like,
correct.
If Q is greater than 1, will decrease in voltage, and if Q is less than 1, will increase in voltage.
Exactly right. Exactly right. Yep. Yep. Because remember, if Q is less than 1, that means you've increased the concentrations of products relative to reactants. So that makes it less spontaneous. If Q is greater than 1, sorry, did I say that right?
I think so.
If Q is
less than 1, you've increased the reactants more than the product.
Sorry,
right?
the reactants more than the product. I know Q product. No, if Q is less than 1, no. If Q is, yeah, that's right. That's right. Reactants more than products, right? Because it's, in this case, right, we've increased the concentration of, compared to standard conditions, we've increased the concentration of reactants relative to, concentration of products relative to reactants, right? Which makes Q greater than 1, which makes the voltage lower. Okay.
Awesome. Thank you.
All right, good. All right, let's have you try one. Very much like the problem we just did.
Do we use the same equation as before?
Really quick, let's identify the reaction that's happening here, right? The way you do that is you look at which one's more negative, and that's going to be the oxidation, right? Negative is oxidation. So look at the more negative one, that's going to be the oxidation. So magnesium is going to magnesium 2 plus, right? And Fe 2 plus is going to Fe. Okay. So just a little hint in case you're getting stuck, E cell, right, is going to be equal to E cathode minus E anode. Figure that out first. And then you're going to take, sorry, that's going to be E zero cell, E cathode minus E anode. Figure that out first. And then you're going to take that E cell and you're going to plug it into here, right? And you know that the overall reaction is magnesium solid plus Fe2 plus aqueous goes to magnesium 2 plus aqueous plus Fe solid. So based on that, you can get an expression for Q. All right, plug that in, calculate E cell. Okay, I'm gonna call time here in just a few more seconds. So if you want to try to put in an answer, go for it now. All right, so the right answer was A, and the majority of you got A. That's good, but a few of you got B or C. So B was just E0 cell, right? E0 cell was not what it was asking for. E0 cell is E0 cell is the voltage under standard conditions, right? Which you calculate by doing E cathode minus E anode, right? And you know this is the cathode. Why? Because it's the more negative, right? Negative is oxidation, okay? So, so how do you figure out E cell? Well, you got to use E0 cell minus 0.0592 over n times log of Q. So if we plug those numbers in, we get 1.92 volts minus 0.0592 over 2, right? 2 moles of electrons transferred here, times the log of, now here you got to be a little bit careful, right? It's products over reactants. So the concentration of magnesium 2 plus, right, which is 0.200 molar, divided by the concentration of Fe, which is 0.05. Okay, so if you work that out, that ends up being 1.90 volts. Okay, again, you see that there's not a huge change in the voltage, but there is a small change. Let's see if it went in the direction we predicted, that we would predict, right? So it went from 192 under standard conditions, it went a little lower, so it got a little less spontaneous. Does that make sense? Well, let's see what happened. We decreased the concentrations of both Fe and magnesium 2 plus compared to standard conditions or standard states, right? Standard states would be 1 molar each, but we decreased the Fe more than the magnesium, right? So that now the concentration of the Fe is less than the concentration of the magnesium. So according to the Chatelier's principle, we'd expect that to make the reaction go left. So it'd be less spontaneous than it was under standard conditions, right? If it's less spontaneous, we would expect a smaller voltage, which is in fact what we got. Woo, lots to think about there, right? Do you have any questions? Any questions on any of this?
Well, to solve for Q, will we always be given the molarity? You know how you do it for magnesium and iron.
You need to have the, if you have non-standard conditions and you want to calculate E cell, you have to know what those non-standard conditions are, right? So you have to be given the molarities. Any other questions?
We could also be given like pressure or temperature as a non-standard condition.
Pressure if it's a gas, yes. Not temperature, not really.
Okay.
Yeah. N is the number of electrons transferred. So what you want to do is you want to look at the redox reaction, make sure it's balanced, right? And then see how many electrons are transferred. Okay.
And then we just added both reactions. Like, I guess my trouble was kind of figuring out at the beginning how to set up the equation I was using the equation we used on the last slide, but.
You mean the equation for the redox reaction?
Yeah.
Yeah, so the way you would know that from the half reactions is you take the more negative one and make that the oxidation and then add them together. Okay. All right, very good. We are out of time for today, so I'm going to officially end class. But of course, like always, I'll stick around and answer any questions you might still have on this or on any other material. Thanks for being here today, and I'll see you all on Wednesday. Bye.